Okay, I'm going to try something new today. I'm going to try and do this off the whiteboard as opposed to the smartboard. Hoping this will be a little more visual, that's all. So I'm not going to be able to go over as well with some of the reading, but you should have the reading in front of you. You should read through it, and I can jump straight into the examples here. Example 1 is asking us to simplify each quotient using the quotient property of radicals. And they give the fact that x and y both need to be greater than 0. So again, this is review. This should be fairly straightforward. The square root of 8 over the square root of 18, right? Just using the quotient property, we can rewrite that as the square root of 8 over 18, which then we can simplify that fraction, which would be the square root of half of each, 4 over 9. Which again, our quotient property can put us back to the square root of 4 over the square root of 9, and that will come straight out to 2/3. So that's the long drawn out way we could possibly do it. Hopefully we can take a couple little shortcuts away to make our work a little less. Example B, if you look at this in your paper, this is the example here, and the answer here is this is simplified. It's as far as you can go. But if you look at the answer key on that worksheet you have, it does say it can be simplified because they forgot to put in that symbol. So this is actually supposed to be the square root of 10 over the square root of 5. And again, we can just use the same properties. Square root of 10 over 5, which simplifies to 2. So square root of 2, or 2 over 1. But there we go. That is our final answer. Just race through a little faster. So it's square root of 225 over the square root of 3. I would jump straight into, right, 3 out of the 225 would put me right to the square root of 75. That's the way I write that, quicker, little less work showing. And of course, this is not simplified. We can simplify the square root of 75 further, right? So again, if I need to, square root of 25 times the square root of 3. And that, of course, becomes 5 root 3. Again, you might notice I'm not doing all the examples here. If you do have a problem with that, let me know in the comments section. But just going to the last one here, so we have a little more going here. We have square root of 24 plus the 2 times the square root of 60 minus the square root of 3, all is the numerator, and the square root of 3 is the denominator. And again, the key with this one, as I always like to say, is remember that the fraction line, right? So from here to here, I call those implied brackets. So basically, this is all in brackets, everything above that line, which means that if I want to remove the square root of 3 out, it has to be a factor of every term above. So is square root of 3 the factor of the root 24? Yes. Can root 3 be factor of root 60? Yes. And of course, root 3, root 3. So we can look at this one at a time. So root 24 divided by root 3 is going to equal the square root of 8. 2 times root 60, we can divide by root 3 and get 2 root 20. And then negative root 3 divided by root 3 is going to be negative 1. And that's how we're going to do that. Am I done there? As it turns out, no, I am not. Of course, can simplify a little bit further here, right? Square root of 8 can simplify to root 4 times root 2. Root 20 can go to root 4, root 5. And then we can simplify this one less step, which we had already learned in a previous lesson. So this becomes 2 times the square root of 2 plus 2 times the square root of 4, which is 2, which is 4 root 5. Minus 1, and there we go. We've simplified these ones as far as we can go. Let's take a look at the next example. Okay, and so here's our second example. Here they're asking us to rationalize the denominator. Of course, the reasons for rationalize the denominator are explained in the writing as well, so I'm not going to get into the reasoning for why we're doing it, but yes, there is reasons why. So this is, we don't like having a rational value, or irrational value, sorry, as our denominator. So we need to get rid of that. Of course, we can change the value of anything, but if we multiply it by 1, we're not changing the value. So, right, any fraction like a over a is equal to 1, right? X cubed over x cubed is equal to 1. Right, 3xy times pi squared to Euler's number, again, times 3xy pi squared e. Again, it's still equal to 1 as long as our numerator and denominator are the same. So we can multiply by whatever we want and still not change the value. So 2 times over the square root of 3. The best way to get rid of that root 3 is multiply it by root 3. To keep this an equal value, I'm just going to multiply by the square root of 3 over the square root of 3. So, whoops, and I put that in there, that should be times. So 2 times the root 3 is 2 root 3, and then root 3 times root 3 is just 3. There we go. Same value, you can check in your calculators, but we have now rationalized our denominator. Same thing here. For example B, I'm just going to multiply by that same value. So 2 square root of 5 times the square root of 3 is going to be square root of 15. And square root of 3 times the square root of 3 is again going to be 3. The question is, of course, can I simplify this radical anymore? That's always something we got to check into, right? So we got to look at our perfect squares. 1, 4, 9, 16, no. So that one's already simplified as far as it goes. For C, now we're looking at this situation. We have 3 times the square root of 5 divided by, or over 2 times the square root of 3. So there is a couple ways we can do this, but there is an easier way, right? I can multiply this by 2 times the square root of 3 over 2 times the square root of 3. I get 2 times 3 is 6, root 15. And I go on the bottom, I got 2 times 2 is 4, times root 3, which is 4 times 3, which is going to be 12. Then I'm not done yet, because I have coefficients or constants, which can be simplified. So 6 over 12 can simplify to 1/2. So root 15 over 2. Now, of course, that's not the only way. There is an easier way to do that. If we can recognize that we take the exact same question. If I just want to get rid of the irrational number, that's the problem. I don't want to necessarily try to get rid of everything. I can just multiply this by, again, the square root of 3 over the square root of 3. That way I'm only getting rid of that rational. And that can sometimes make less simplifying, or it can just remove any simplifying at all. So 3 root 5 times root 3 is 3 root 15. 2 root 3 times root 3, so 2 times 3 is 6. So I end up with 3 root 15 over 6. Again, this one can still be simplified further, but divided by 3 top bottom root 15 over 2. I will, in fact, get the same answer. So again, you don't have to go by the entire denominator. You can just get rid of the irrational value you want to get rid of. So that's what I'm going to do for this next example, of course, is I'm just going to try and get rid of the square root of 2. So I'm going to multiply by root 2 over root 2. So that becomes negative 4 root 12 over 3 times the square root of 2 times the square root of 2, or 3 times 2 is 6. There's a couple things happening here. I can simplify the fraction, and I got to recognize that square root of 12 is not a simplified radical. I can simplify that further. So I can break that into a 4 and 3, which is 2. Root 4 root 3 over 6. And of course, I'm probably going to walk myself out of room here. This will be ugly, so apologize. This becomes negative 8 root 3 over 6. And of course, the 8 and 6 can simplify further. Becomes negative 4/3. Negative 4 root 3/3 to simplify to the max way. So that is going to be our intro to rationalize the denominator. So give that a shot, and we will take a look at our next example. Okay, as we come into our third example from our notes, the only thing we have to look back at restrictions, right? So our Anything under the radical symbol, any variable under the radical sign cannot be a negative value because we cannot have a negative radical. And our denominator of an expression cannot be 0. So there's two things we got to look at here. Is the fact that x must be greater than or equal to 0 because it's in the radical symbol, and because it's the denominator, x cannot equal 0. So we can combine these two into one expression, which is just that x has to be greater than 0. And that was not a good bracket to use. So that's going to be our final restriction, right? Otherwise, we proceed as normal, right? We want to rationalize the denominator. Which we have done here. It just, we would need to state our restrictions with that, where x has to be greater than 0. The next one has a little bit of a complication to it that I'm not going to get to. We're going to keep this one straightforward and simple. I'll give you a quick glimpse into what the issue is, but normally I like to find my restrictions first, but this time I will in fact rationalize by denominator. Again, the x, y are the ones that are irrational, so I will get rid of the irrationality by multiplying by the square root of xy again. This gives me 3 root x y squared over 2xy. I can simplify the radical. I have a y squared in there, so that becomes 3y root x over 2xy. That brings light now that I have a y above and below. So boom, boom, those two can go, as they are going to be equal to 1 anyway. So 3 root x over 2x is going to be my final. For this one, again, the same thing is going to happen here. The x has to be greater than 0. The y has to be greater than 0 for the same reasons as above. So x must be greater than 0. Y must be greater than 0. The complication here, and we're not going to get into this, is because you have an x times y. So if x was a negative value and y was a negative value, then we could in fact find there is a possible answer for that radical. But we're not going to get into that right now. That's a complication we can deal with later. I think we might even touch on that when we hit absolute values a little more coming up. We start looking at exceptions and how to post which rules apply when. But for now, that should be more than sufficient of an answer as we get ready to move to the next example. For example 4, they're asking us to find the conjugate. So again, this is setting us up to what we did in the past. Like this is our finding the difference of squares. And our difference of squares was the conjugate pairs, right? So again, 3 minus the square root of 5, the conjugate would be, right, the initial value. If this is an a and a b, so if this is a, b, if this is a plus b, then we go to a minus b is the conjugate. If this was a minus b, then a plus b is the conjugate. So we keep the initial term the same, and we just flip the secondary term. So this would become 3 plus the square root of 5 is the conjugate of this one. For here, our conjugate is going to be square root of 3 plus 1. For 2 plus the root of 2, they're going to say 2 minus root of 2. The next one is the one I do want to take a closer look at. The way they show you how to do this in the notes guide is not incorrect. It's absolutely correct, right? The first term stays the same. It's going to be negative root 5, root 7. For this example, the one thing we're going to learn, especially when we go into rationals, is our lead term should be a positive value. So technically what we should do is we should turn this one into negative. So if I divide out negative 1 from both and put in brackets, this would be negative root 5 plus root 7. This would be the same term. It's just we divided out the negative 1. Now the conjugate of this would be, so the conjugate of this becomes root 5 minus root 7, which is, now you're looking up here, well, these two are not the same. But again, because this is going to be the lead term here, again, if we're looking at our first term being the negative value, we would want to get rid of that as well. Divide out negative 1 here, and that would become root 5 minus root 7. So we are in fact getting the same answer. I just strongly recommend for ease later on, we should start looking at maybe thinking about keeping our initial term or first term in a positive format. So that would be example 4, just to get us set up for our next lesson here. Okay, so moving on to example 5. If you've probably noticed here is I've skipped B and C. Hopefully we can get enough of using A and D of what we're going to do here. And this is just, again, using our knowledge of the difference of squares and what happens to cancel things out. And we can make this more appropriate for what we are doing here. So again, I want to rationalize a done number. Again, this is the implied brackets, right? So the root 5 minus root 2. I can't just reply. If I multiply by root 2, then I'm going to end up with a 5 root 2 minus 2 answer. And I still have an irrational denominator, so that is not going to work. Instead, what I'm going to have to do here is multiply by the conjugate to get rid of all of the irrationals on the bottom and to give us the rational denominator we're looking for. So I am going to have to say, well, the conjugate is 5 plus root 2, and that's what I'm going to have to multiply by. Again, so we're looking at implied brackets here, which, I mean, I like to draw them in when I'm doing this just because that clarifies it for me. My implied brackets of my fraction lines to show me exactly what I need to do. Now I know it's 2 times 5 equals 10. 2 times root 2 is 2 root 2. Now, because I have a binomial times a binomial, I can do this once and one time only. I'm going to do the entire write-out, and then I'm going to refresh why I'm not doing this later, right? So 5 times 5 is 25, right? 5 times root 2 is 5 root 2. Negative root 2 times 5 is minus 5 root 2, and negative root 2 times root 2 is going to equal negative 2 or negative root 4. Let's write the negative. If I'm doing the whole thing, let's write the whole thing. Again, and this is why are we multiplying by the conjugate? Well, this is the reason. This whole plus 5 root 2 minus 5 root 2. We did the conjugate because those cancel each other out. And we know that, and we are left with a way more usable value down here, 25 minus root 4, which is 25 minus 2. That's the reason we multiply by the conjugate. That's why the difference of squares is very important for us. Then all we have to do from here is simplify this as far as we can. So the 10 plus, that is simplified as far as it goes. The 25 minus 2 becomes 23, and there we go. We have our fully simplified term. I'm jumping down to D just because, again, we're just doing the exact same thing, but it's just going to be a binomial times a binomial on top and on the bottom. So again, I want to get rid of this. I want to rationalize. So I got to first find the conjugate of this. There's my conjugate. I want to not change the value, so I have to multiply both. Just to help myself visualize and clarify, I'm going to draw in my implied brackets. Now I can straight up see that it is a binomial times a binomial. So 3 root 2 times 2 root 2. 3 times 2 is 6 root 4. 3 root 2 times negative root 5, negative 3 root 10. Negative 5 times 2 root 2, negative 2 root 10. And negative 5 times negative root 5, again, that's going to be negative root 25. Later on, again, as I'm learning through and I get good at this, I'm going to jump straight to the 12 here. I'm going to jump straight to the 5 here. I'm not going to rewrite more than I have to. In that context, I'm going to do that jump right now with my conjugate. I'm going to take the 2 root 2 times 2 root 2, 2 times 2 times root 4 times 2. So 2 times 2 times 2, that's going to be 8. I can get rid of the, I don't have to worry about doing this and this because they cancel each other out. So I can just jump straight to the the lasts, root 5 times negative root 5 is just going to give me minus 5. So if you can make that leap, take that shortcut, life gets way simpler. I did leave myself a little bit of work over here, of course, so 6 root 4 is going to be 12. I'm not running off the board, am I? Minus 3 and minus 2 root 10s is going to be minus 5 root 10. Minus the root of 25, so minus 5. Over 8 minus 5 is 3. And again, I'm running myself out of board here. So I can combine like terms again, right? So 12 minus 5 root 10 minus 5 will leave me with 7 minus 5 root 10 over 3. The 7, the 5, and the 3, those are all coefficients constants. Do they have a common factor? No. So that will therefore be simplified as far as it goes. I did make a mistake, didn't I? I hope you caught what I did there. I did it on purpose, again, like my usual routine, to see if you were paying attention. I took a negative root 5 times a negative root 5, and I got a negative for some reason here. So that should be a plus. That should be a plus. So it should be 12 plus 5. There we go. 17 minus 5 root 10 over 3. Right? Even as math teachers make mistakes sometimes. It's all okay. So again, I still can't simplify that any further, but that would be my final answer on that one. Which means I think we only have one more example to go through, and you're free to work through. So I'll set this up and I will speak to you momentarily. Okay, through the magic of TV, I have the next and final example here. I'm not going to do B again. I want to keep this a little shorter. If you do still need me to go through another example, if you want me to go through 6B, again, just put in the comments that you'd like to, and I could post that. Here we go. Now we're looking at, we have a rational, so we have a denominator which cannot equal 0. We have a rational, so we have a variable under the radical sign which cannot be a negative value. So the best thing to do is to think about these conditions before we start, because it's going to be based on the original equation, not what we come up with in the end. The two should match, and they often do, usually do, there's rare exceptions, but we need to cover our butts now. So we need to know that both x must be greater than or equal to 0 in this context because the radical. Now we have to look at the denominator, which means for the denominator, 2 plus the square root of x cannot equal 0. And then we just solve this like a regular equation, algebraic equation, to see what does that mean for x. So we're going to subtract 2 from both sides, therefore the square root of x cannot equal negative 2. We square both sides, so x cannot equal 4. So that's going to be our two restrictions. X must be greater than or equal to 0, and x must not equal 4. So we got our restrictions. Let us continue and take a look through what we can do here. So more just rationalize the denominator. I'm going to multiply this by the conjugate. Right over the conjugate. Again, Mr. Lukey likes to draw his brackets, apparently. And then I just work through. 3 times 2 equals 6. 3 times negative, so negative 3 root x. Negative root x, so minus 2 root x. Negative root x times negative root x, so plus x. Again here, the first 2 times 2 is 4. Because I'm multiplying the conjugate, I'm just going to the lasts. Then root x times negative root x, 4 minus x. Now I just got to simplify and I'm done. So 6 stays with that. It's spoken for. I got 2 root x, so this would be negative. So that one and that one are spoken for. Plus x. And the 4 minus x equals the same here, so I'm simplified as far as I can go. I'm going to state my restrictions again at the end. So x must be greater than or equal to 0. X cannot equal 4. Sub in the 4 real quick for the x and see what happens to my denominator. It becomes 4 minus 4 is 0. That makes sense. And it matches what I had in my original restrictions. So that's it. That's the examples. hopefully this helps get some work done along the way. Email me if you have any questions, and have some fun doing your maths.